Good afternoon, sir. This is our research output about the effect of trim and stability of a ship in the event of damage due to flooding. The group This group is composed of Chano Junior si Jenny B, Shokon Jan Caril, Emerson Celia, Serapion Jatro Moses, Tante Christian Luis, Severino Patrick.
Introduction. In other words, whatever theories and cases of stability we have dealt with have, till now, considered the hull of the ship is intact and does not allow ingress of seawater into any compartment. Remember how we introduced the concept of stability in the first article of this series? That there are two major types of stability that concern surface ships: intact stability and damaged stability. This article will deal with the latter.
Discussion. The study of damage stability of a surface ships come of use when the ship's watertight hull is affected in a way that allows water to flood any compartment within the ship's hull. Since this changes the stability parameters of the ship, the extent of which depends on the extent of damage and flooding, it is studied separately from intact stability. Before going into the methods that are used to evaluate the damage stability of a ship, we will discuss the effect of flooding on a ship. Change of draft. Flooding results in entry of water into the ship's damaged compartment. This will cause a change in draft to the point where the displacement of the undamaged intact part of the ship will be equal to the displacement before damage, less the weight of the water that entered the ship after flooding. To express it, change of trim. Ingress of water in a compartment can be considered as an addition of weight to any point along the length of the ship. This causes a change in the trim of the ship. Healing. The ship will heal if the damaged compartment is unsymmetrically positioned about the center line of the ship. If the metacentric height of the ship is in the flooded condition is negative, the damaged ship is rendered unstable. In such a case, the ship would capsize if the flooded compartment is unsymmetrical about the center line, and is prone to capsize by action of any external healing moment if the compartment is symmetrical about the center line. Change in stability. The metacentric height of the ship changes due to flooding. This can be explained by the general expression of metacentric height. The explanation of reduction in stability can be done in two ways, which is exactly what we will study in this article, but at a later stage. For now, it should be suffice to understand that when a ship is flooded, it results in a change of KB and BM values. The KB rises due to flooding, and it may rise further due to change in the ship's trim. However, there is a significant reduction in BM, which is function of the area moment of the ship water's plane. Why? We will look into that when we study the loss buoyancy analysis. Change in freeboard. The increase in draft of the flooded ship results in reduction of freeboard, which poses of a great threat to the residual buoyancy of the ship. Even though the mesocentric height may be positive after flooding, reduction in freeboard to a point where the deck is immersed decreases the ship range of stability. This means that the ship could now capsize due to external forces of wind or waves. Loss of the ship. One of the most common terms that is used in damage condition of a ship is margin line. The margin line of a ship is an imaginary water line considered 75 mm below the uppermost continuous watertight deck. If a ship is damaged, it is considered to be safe only if the margin line is not immersed. Once the water line reaches the margin line at any point along the length of the ship is considered to be unsafe and evacuation becomes mandatory. Evaluation, damage stability, equilibrium condition. The most important step in analysis of a damage condition is to calculate the equilibrium condition, which include the final trim, heel, and draft after the location and extent of damage is known. There are two methods that are used for this purpose. We will only graze through the concept of each. Loss buoyancy method. This method assumes that the damaged compartment does not contribute to the total buoyancy of a ship. Hence, the ship loses a part of its total water plane and its buoyancy. Therefore, reducing stability, this method is easier to use because it is not iterative. On the other hand, the result obtained from this method are slightly less accurate than the other method. Added weight method. The added weight method considers the flooded water to be a weight added to a certain point in the ship. The problem is solved like a traditional weight addition case, and the trim and draft are calculated over a set of iteration Though this process is time-consuming, it produces more accurate results and is hence used by most stability analysis software.
So, for conclusion, therefore, we conclude that the reduction in metacentric height due to the damage can be extrapolated to the stability curve as a reduction in height of the GC curve and range of stability, as shown in the figure above. So if the loss in metacentric height is such that the remaining maximum righting lever, GZ, is less than the healing moment, the ship will capsize. It is therefore the designer's work to A. Design the subdivision in such way that the remaining righting arm is sufficient up to a certain level of damage. B. To identify the extent of damage that can be considered safe for the ship. Traditionally, a ship is divided longitudinally into a number of watertight compartments to restrict the flooding to one or more compartments in case of damage. This prevents progressive flooding. The compartmentalization is done by means of transverse watertight bulkheads. But the interesting question that arises here is, how many watertight bulkheads would a particular ship require? How many compartments do we divide a ship into? These are answers that need to be answered at a very initial phase of the design, most usually in the concept design phase.
For recommendation, we recommend the only time a vessel can be assumed to be stationary and in upright position is when it is in dry dock or before it is launched to the sea. Once it in the sea, the ship has to sustain different environmental conditions along with the effect of various external and internal changes. A ship is always acted upon by several forces from actors such as seawater, wind, internal mass weight, free surface effect, etc. Thus, it is of utmost importance for a vessel to always remain stable afloat in all conditions. A stable ship. Ship stability can be defined in simple terms as its characteristic or tendency to return to its original state when an external force is applied or removed from the ship.